Welcome everyone. We all have worked or are working in companies which start small and have a monolithic app built as a single unit. And you're doing such an amazing job that the traffic grows on the system and the monolithic app runs into all kinds of scaling issues and it starts to fail. So what do you do now? You do the right thing. You break your monolithic app into multiple microservices, which are easily horizontally scalable and have great fallbacks. But you don't worry much about your backend data store. You continue to fit your microservice use cases into the originally chosen backend. And very quickly, things become complicated and complex at the data tier. And your data team feels something like this, because they are the ones who are managing the uptime of your data stores. Now imagine, instead of trying to use one data store for all your microservices, you leverage the features and the strengths of the backend data tier to fit your microservice needs. Then your data team can be peaceful and in a state of zen. Hi everyone, welcome. Today we'll be talking about polyglot persistence at Netflix. I am Rupa Tangirala. I manage the cloud database engineering team here at Netflix, and we provide persistence as a service for whole of Netflix. Briefly about Netflix. Netflix has been leading the way for digital content since 1997. We are over 117 million subscribers and growing internationally, bringing great viewing experience across many devices and bringing to you great original content in the form of Stranger Things, Narcos, and many more. All the interactions you have with Netflix, be it your membership information, your viewing history, your profiles, your bookmarks, all the data which is needed for the movie to go from script to screen and beyond is stored in some shape or form in one of the data stores we manage. Introducing to you the cloud database team at Netflix, CDE. We have polyglot persistence, as I was saying, and we have wide variety of data stores. Cassandra is our primary data store. It's a NoSQL distributed. It's highly available, and it's used as a source of truth for most of our microservices. Then we have caching solutions in the form of Dynamite and EV Cache. Both are distributed in-memory caching solutions. We also have Elastic for our needs for real-time data search, ad hoc search queries, and ability to visualize that data in near real time. Leader recollection, Apache Zookeeper, and some MySQL for transactional use cases. We use MySQL. And many forms of RDS, like there are some applications which really need high transactions, so we have multiple flavors of RDS. And some data is also stored in S3. And we have Janus Graph. So over the years, we have been doing quite a lot of meetups. We started with EV Cache, which was started around 2010. And then we embraced Cassandra, and over the years, we have been giving talks about how Cassandra has been working great for us behind the scenes when it's doing the replication. We use it for active-active, as well as how are we doing upgrades at scale in Cassandra. We've also been talking about Elasticsearch, how at Netflix we have given multiple talks on which use cases have we been using for Elasticsearch and what are the challenges the infrastructure team faces. And also about Dynamite. Dynamite was built in-house, inspired from Cassandra, and it supports Redis, Memcache, and RocksDB, so it's a pluggable data store. We have been using TitanDB for graphing solution, and you will get a deep dive this meetup, and you will get to know how, in the agenda briefly, how we are doing the service, like how does all the microservices, how do they interact? How do they look at the cost of their clusters? How do they do schema changes? How do they look into the data, right? So you will get a deep dive into the CDE service and the data explorer. CDE service is our self-service portal from where users can create clusters and do many things, which the team will be covering. You'll also look into what we have been doing in the area of repairs. Repairs in Cassandra are very painful, and if you're using Cassandra, you would know. So you will get a deep dive into where we are at with it. Also the changes in Memcache Flash, very interesting work being done there, and how we are replicating caching data across region. And lastly, we'll end with our graph database. How have we evolved from TitanDB, as I was showing, to Janus Graph? So with that, let me introduce Kunal, who is our platform UI and engineering team. Kunal, welcome.
Right, thanks, Rupa. So hi, my name is Kunal Kundaje, and I'm a software engineer on the cloud platform team at Netflix. So today I'm going to talk to you about CDE service, which, like Rupa mentioned, is basically our central hub for all of the interactions that the rest of the engineers within Netflix have with the CDE team. So before I dive into what CDE service is and some of the use cases, I wanted to go briefly over the motivation for why we even started this effort in the first place. So you look at a bunch of these icons, you're probably familiar with a lot of them, right? So this is kind of like all of the different tools that the CDE team used to use and still uses to some extent while they were dealing with managing this large fleet of Polyglot persistent stores. So requests for new clusters and like changes used to come in through like emails, Slack messages, Jira tickets, so on. Customer data used to be managed in Google spreadsheets. And then automation was running in Jenkins jobs, SSH scripts on instances. Alerting used to be in our Atlas alerting system, dashboards. And then there's Archaeus, which is our configuration management store. So lots of these different tools, right? And so you basically have our engineers sort of going into all of these different tools when they need to make any changes. So we built CDE service as basically the central hub for all of these persistent stores. And it supports like most of the Polyglot stores that Rupa was talking about earlier. So CDE service covers three aspects of operations. So there's the self-service aspect, which deals more with how the rest of the engineers within Netflix actually use the system. There's the management pieces, which are centered around the use cases of the CDE team itself. And there's insights, which go beyond the things that you're normally used to, like read, write metrics and so on. So we'll cover some of these as we go along. So let's look at the first scenario, right? So this is the self-service aspect. So one example of this is Elasticsearch cluster creation. So this is what the workflow used to look like before we had this, right? So users used to send requests via email, Slack, or Jira tickets. CDE on-call would then translate their requirements into something that they could apply to their automation scripts and then kick off this automation to create these clusters. And then once the clusters were created, the on-call would have to notify the users via email, include information about how to access the cluster, set up security groups, useful links, all of that stuff. So that's what it used to look like before. So this is the Elasticsearch cluster creation page in CDE self-service. So this is open to all engineers within the company. So they can go in basically and just create a new cluster whenever they need one. And all of the information we actually ask for is things that are directly relevant to them. So this doesn't include like underlying parameters to the automations and so on. So they pick, for example, like which regions they want the cluster in, like what the data size is. And under the covers, the CDE service basically translates all of these user requirements into parameters to our automation. You also get like a nice little preview of like what the estimated cost is going to be. This is purely illustrative only. And then once the cluster actually gets created, the user are notified via email automatically, and they get to this cluster landing page, which gives them a lot of summary information like the cluster's topology, links to some of the plugins. In this case, like we're linking to some of the common Elasticsearch plugins like Kibana, Cerebro, links to our Lumen dashboards and so on. And there's a bunch of tabs along the top that allow you to do other things as well, and we'll cover some of those things as we go along. So once the cluster has actually been created, there's also the whole aspect of managing your indices on them, right? So this was the second phase that we looked at from a self-service perspective. So again, this is what the before scenario used to look like. So index templates were still managed by the users, either directly using the Elasticsearch REST API or through plugins like open source plugins like KOPF or what it's called. It's called Cerebro now. And then retention policies and backups, on the other hand, were managed by the CDE on-call. And they did this by running Jenkins jobs to update configurations in RKS, which is our configuration management system. It was difficult to like quickly find out which index collections were missing templates or missing retention policies. And we consider all of these to be sort of best practices so that your cluster doesn't grow indefinitely and your indices don't have mappings that you didn't really expect to happen. So we wanted to get all of this stuff together. So this is what the index management looks like in CDE service. So you basically get a list of all of the collections that are on the cluster, along with statistics about like what the number of indices in those collections, the sizes. But we also have the little icons showing you whether the index collection has a retention period set or if it has like an index template set, and gives you warnings if you don't have any of those. So you can click on any one of these and actually set your retention policies and index templates right from the app itself. The next aspect is cluster management. So this is again talking about things that the CDE team themselves use, not other engineers within the company. So one example of this is Cassandra Repairs, and we'll go into like a really awesome deep dive in one of the upcoming talks. But the goals basically here from a CDE server's perspective were to allow repairs to be enabled and disabled quickly for a cluster. And then allowing fine-tuning of table-specific settings for things like subrange repairs, parallelism, and all of those things. So here's an example of what that looks like in the tool. So you can enable and disable repairs just by toggling the switch on and off. And you see a set of all of the table levels settings here as well. You can edit those and you basically get all of the parameters. You can customize these. Some of these are auto defaulted to sane defaults. The next aspect is cluster backups. So again, this is a similar use case where you want to be able to enable and disable these quickly, as well as customize things like the backup schedules, the retention periods, S3 bucket locations, and so on. And again, this is what that looks like. So very similar UX for that as well. Once you pick one of these, you can actually specify what the cron schedule looks like, the retention period, where we're storing those backups in S3, and so on. And the final aspect is insights. So this is insights, again, like I said earlier, beyond just metrics, which we're already publishing to our metric store Atlas, and we have sort of company-wide dashboards for. But these are more like data store specific things. So like things like cluster cost, right? So this is one of the things that we wanted to provide. So the idea behind this was to provide cluster owners insight into the costs of running their clusters so that they can make informed choices and trade-offs with respect to the efficiency and resource usage. Like, do I really need like a dedicated cluster for this use case, or can I use a shared cluster? And so what are the cost comparisons of things like that? So this is an example of what that looks like. You're looking at a demo cluster and you see a breakdown of like costs for running that cluster, and that's broken down by the whether this is like EC2 costs purely or like things like S3 backups. It's broken down by region, so you can see patterns in that as well. And then there's node inventory. So this is things like metadata collected at a node level. So that, like most of these clusters have like a large number of nodes, and finding out what's running on a specific node by having to like SSH into each one of those would be tedious. So we're basically aggregating all of the on instance metadata and actually aggregating that and displaying it all in one place. So you can see things like the version of the data store that's running on each node, what sidecar versions are running, what the OS version is, AWS instance types, a bunch of other metadata that we collect from the instance itself. And here's an example of what that looks like in the case of like a Dynamite cluster. So you see a list of all of the nodes. There's 150 of these in this particular cluster. You can see that all of these are running a specific version of Redis. But you can see the Florida sidecar there, actually the versions vary across them. So this allows you to find out like what the state of the different nodes in the cluster is without having to sort of go into each machine individually. Finally, I wanted to just give you a quick overview of what the overall architecture of the CDE service looks like. So basically, we have a web UI which is essentially the front end into all of the stuff that I just showed you, and this is built in Vue.js and TypeScript, which we found to be a very productive environment. This talks to a CDE service API gateway layer, which is built in Java and provides standard REST APIs for all of the things that we're trying to do. The gateway then talks to Jenkins to kick off some of the automations that the team already has. So things like the Elasticsearch cluster creation that I mentioned, we're translating the requirements into those parameters and kicking off the Jenkins job behind the scenes. It also talks to Archaeus for managing some of the other configuration properties. And then a lot of the data that we gather from users as well as what the team specifies goes into a multi-region Cassandra store. And then there's these three regional, what we call backends, which are then talking to all of the different data stores across, like all the nodes in all of the data stores that we have. And so the way that actually happens is we have this process called Bolt that is provided by our inside engineering team. And that lets us collect all of those on-instance stats that I showed you earlier. So it basically runs a little process, and then we can collect and aggregate that across the entire fleet. That's basically what the rough overview of what the architecture looks like. So that's all I have for you today related to the CDE service, but we've got a lot more features that we'd like to add and still actively working on it. So with that, I'll introduce Gim. Talk about Data Explorer.
All right, thank you, Kunal. Hi, everyone. Yeah, my name is Gim Hassantan. I work with the Cloud Database Engineering team, and I'll give you a little overview of the Data Explorer. We'll be going into a live demo as well, but I wanted to give you a little bit of background and sort of motivation first. So what we found is that engineers typically want to really focus on building their own apps. They're not necessarily interested in the low-level persistence details. We definitely have a lot of power users that do want to get down into those nitty-gritty details, but generally we want to try and build tools to try and kind of lower that bar to entry. And yeah, and so the CDE team has obviously a wealth of experience here, but we want to try and reduce the support load on them as well. And so if we can build the tools that sort of encourage some of those best practices and minimize the chance of user error, it's really a win-win. So to that end, we started out with building a web-based tool that could try and codify a lot of those best practices. Web-based, since we didn't want to have a client install, and we wanted to provide really a sort of paved path for those super common operations. You quickly want to check for a row, look up some data, and maybe you're responding to an issue. And then finally, to work at scale in the Netflix ecosystem. So being able to discover all the clusters that we have out there and provide integration with all of the other metrics and features that we have. So I'm going to jump over to a quick demo here. So the page you see here is sort of the landing page for the Data Explorer. So this is really the main hub for people to come and access the data. So currently we support Cassandra and Dynamite. And so when users come in here, they can click on a data store type and then go and explore the list of clusters and then pick a specific cluster. So for this demo, I have a Cassandra cluster created already. And I'm going to walk you through a couple of pretty common operations. So for instance here, we can go ahead and create a key space. So creating a key space in Cassandra, there's an opportunity to get your replication settings wrong. Maybe you might not pick all the right regions. Maybe you don't have the right number of racks per data center. So we try to make that, give you kind of common, sensible defaults. We use CDE's best practices. So we've gone ahead and created a key space here. It's completely empty, so let's go ahead and create a table. So creating a table in Cassandra is, again, it takes a little bit of knowledge about the system. So we try to build a workflow that kind of streamlines this. I'm going to create a demo table here. And the page that you see here is the schema definition. So you can go ahead and create new columns. So I'm going to have an ID column. I'm going to specify that as a big int. So now I have one column defined. Let's see, I'm going to have a last name field. Maybe that's a text field. And you can just drag and drop them. So here I'm setting up my partition key as well as my clustering column. And you see that I got a little warning here saying that you're effectively creating immutable rows. So since all of your columns are part of the primary key, you may inadvertently be creating immutable data. So anywhere we can, we try to give those sort of like helpful validation checks. So now I've got 3 columns, and then what you'll see down at the bottom here is the storage layout on disk, as well as a preview. So if I expand this, I can see what the schema definition looks like. So I've got my 3 columns, and maybe I'll specify like a sort direction. And you'll see the preview update with the clustering order. All right, so moving on, we'll move on to the compaction strategy. So this is something that's Cassandra specific. It has a big impact on the performance and health of the cluster. So depending on the type of workload that you have, one is more appropriate than another. So if you're dealing with time series data, you definitely want to use a time window. If you're using read heavy or write heavy, size tiered or leveled might be more appropriate. And so you can just check one of these, and we kind of guide the user through choosing the appropriate one. And then now we're on to the last step, is the settings tab. So if you want to specify a default TTL, or maybe define compression settings. So if you want to bias this table maybe towards space savings, or maybe towards read performance, we'll set your compression strategy appropriately. And then we have advanced settings. For those power users, as I mentioned earlier, maybe they want to enable like row key caching or control GC grace. They have the option to do that there. So the last step is a summary, which will show you what the schema looks like, all of those settings that we filled out, any advanced settings you specified. And so now the table's been created. Obviously, it's empty, but this is the exploratory view that most people interact with. You've got the column definitions, you've got the table properties available to you, as well as sample queries. So if you're coming from a relational database background, it might be surprising to you that you can only query on specific columns that are part of the primary key. So you can quickly go and grab one of these and copy and paste it into your app, perhaps. So that's the exploratory view. We've also got a query view, which is more of a online editor. And this will allow you to do more of those free-form queries. So we have code assist. So if we're doing maybe like an insert, we can insert into Meetup. Demo. And we've got code assist for the various columns that you have. So here we've got a partition key of ID, last name, first name, and I'm just going to add a couple of sample rows. So I'm going to add Jessica Jones, maybe Luke Cage, because why not? So we've got a couple of rows inserted now, and then we can go and play with that data a little bit as well. So over on the left-hand side, we've also given you more of an IDE-like experience. So you can kind of link this properties pane on the left to the table that you're interacting with, so you can kind of see the schema definition, what available sample queries there are live while you're writing your queries, as well as a history of recent queries that you've been playing with, as well as online documentation. So for instance, if you're doing an insert and you can't remember the exact syntax for, say, using TTL, we've got some online documentation that you can kind of refer to at the same time. So here we've got a sample key space. So I've gone ahead and inserted some data. And typically this is the view that people will be seeing when they're browsing. So for instance, I might go and search by a partition key, and now you've got a details pane, so you can bring up the user here. can go ahead and make those updates, and then that'll get reflected. So yeah, so that's a quick overview of the Data Explorer. We're still making a bunch of investments here. But yeah, I wanted to kind of give you a quick overview of that, and then I'll pass it over to the Cassandra team, who's going to give you a more deep dive on the repair service.
Thanks, Kim. That was a nice demo. So far we have seen how we landed in a Polyglot persistent store and how we support the scale by building tools on top of these open source systems, and how we embrace this open source technologies by providing this support. So now let me get into a little deeper of how what we are doing in Cassandra space to make Cassandra operators' life easier, so that we can provide Cassandra as a service to the rest of Netflix. And as part of that, we built a service called Repair Service. But before getting into details of the repair service, let's understand the need of one service, something like that. So let's imagine we are watching a show, Netflix original show called Dark, which is a German-based show, and it's pretty popular in German and international markets as well. So since it's a German show, we decided to watch it in German subtitles just for the fun. And maybe halftime into the show, we have seen our subtitles have changed back to English, which is a bad user experience. Now let's take a little pause there and see what could have happened in the backend services. Being in microservice architecture, one could imagine there might be a preference service which is responsible for storing user preferences and also serving the user preferences. Well, maybe that the preference service might have failed to either persist the data or might have got the stale data. And as many of you know, most of our data, Netflix metadata stores, is persisted in Cassandra. Let's get into details of what could have happened with the Cassandra in that scenario or in that incident. So, well, when the persistent service tried to, when the preference service tried to insert this row, it might have only applied to half of the nodes and might not have propagated to all the nodes. Or maybe the other scenario could be the preference service tried to delete the row which is English preferences and update the row with the German subtitle preference. But due to some other repair issues, the data got resurrected and you got English preferences again. Or maybe at the time of this preference is being persisted, maybe your nodes are under network pressure or some other resource pressure, and hints were not paid back. And until recent versions of Cassandra, hints were not that robust enough as well. And Cassandra provides several hooks to alleviate all these issues that we are talking about. But even enabling those hooks comes with the cost. So you might not be enabling inline read repair kind of thing on 100% of the traffic. So if we talk about this, there could be many more of such scenarios. But is there a solution? Yes, there is a solution, which is basically a Cassandra repair, which is an anti-entropy operation, which ensures your data is eventually consistent in your Cassandra backend store. So what does repair do? It's basically reads the entire data from the disk and calculates the hash of it and builds a Merkle tree on top of it, exchanges that Merkle tree with the peers, and does a consistency check and fixes any inconsistencies in the data. Well, seems like a simple process, but it's not actually that simple because it is a heavy resource-intensive operation, and it involves a lot of disk I/O, a lot of network, a lot of CPU-intensive operation. Well, can we make it better? Yes, we can make it better, but one needs a master's thesis in the Cassandra world or Cassandra repair world to make it and to fine-tune it perfectly to work with that scenario at that given point of time. Because as the data changes or usage pattern changes, all the tunables that you did might not actually work anymore. And there are several tunables to make repair efficient in Cassandra, but you need really high Cassandra skills and Cassandra repair details for you to make it better. So let's see how everyone approaches this in the open source world, or even in Netflix when we started, right? So imagine, as I said, it's a scheduled operation which runs on a scheduled basis in your Cassandra clusters. So maybe someone starting with a cron scheduler, or system like a Jenkins, which provides a default scheduling stuff, and does a precise ordering of your repairs on your Cassandra cluster, so that you get all the nodes in Cassandra gets repaired properly. And as I mentioned, it's a heavy resource intensive operation. So any repairs could take maybe hours to days to weeks, and sometimes months together. So when it is taking that long time, you are actually demanding high availability from the solution that you chose. So if it is a Jenkins, you are expecting your Jenkins to be up and running 100% of the time, all the time. And you're also expecting your Jenkins not to have any network partitions or any network glitches. Let's say if you have any network glitch or any network partition or any issue with the Jenkins, either your repair could get stuck or your repair could fail. So maybe you build a monitoring on top of it, so that you are monitoring your Jenkins or your cron scheduler all the time. So now this monitoring system also has a loopholes, because network, it's not resilient for the network glitches, or it's not resilient for partitions. And then as a result, you get pages, and most of the times those pages could be false positives. And when these long-running repairs fail, they need a manual intervention for you to restart and resume the failed repairs. And also, as I said, there are so many tunables that you can work with, in terms of choosing which subrange to work, so that you have a very less of data that is being exchanged between the nodes to make the data persistent. Or if you choose a bigger subrange, maybe you'll have a bigger lot of data which is already repaired that is being transmitted between the nodes. This is called overstreaming and understreaming issues within the Cassandra repair itself. So, well, I took a snippet of one of our bad behaving clusters in our test and prod environments. As you can see, there are so many failures before actually you get one successful repair. Of course, we built a little bit of intelligence into it, where when the repair fails, it continues where it left off and it resumes and all that stuff. But still, you have a lot of pain when you are getting the repair working properly, when you don't have a proper design in place, which is single machine trying to orchestrate thousands of nodes and hundreds of clusters, and trying to make the petabytes of data consistent in your fleet. So that is when we took a step back and tried to see the problem from a different angle. And instead of building automation on top of automation, tools on top of tools, why don't we build a service which could be potentially part of Cassandra, and which does it automatically? Like repair and anti-entropy is something that database takes care of itself, instead of letting operators fight with it and make a war with it. So when we started building a repair service, we had on a high level, we had 4 design goals, which is availability, reliability, efficiency, and scalability. So let me invite Joey to get into details of how we built this service and how we achieved it, and what are the wins that we already have in last 6 months when it is running in production. Thank you.
Thanks, Vinay. So I'm Joey, I'm an engineer on the CDE team, and I'm going to now tell you how we achieved this. So the way we achieved those goals was we started with a rock solid design. So as opposed to like the central coordinator, single point of failure, very brittle systems that we were using before, this time we designed it as a fully decentralized shared nothing system, kind of taking inspiration from Cassandra itself, right? So there's no central coordinator, it runs on the Cassandra host itself, and all coordination is done through Cassandra itself. So this means that we have no dependencies on external services being available. This means that we get to kind of piggyback on the great availability that Cassandra already provides us. And as we've currently designed it, it uses JMX to talk to Cassandra, but that's not actually, I think, a core part of it. All right, so how do we actually achieve 24/7 availability? The first step was kind of rethinking about Cassandra Repair, not in terms of like we run it a Tuesday at 2 a.m., because you've got writes. Do you guys only take writes at Tuesday at 2 a.m.? No, yeah. We take writes all the time, so we should be repairing our data all the time. And by kind of constantly exercising the repair code path, we're able to ensure that the cluster is capable of handling the repair load. So those, whether it's disk load or CPU load, if we're doing it all the time, constantly, then we know that we can, that we'll be okay during peak. But the second big change that we had to make was moving to kind of this notion of shared nothing timeouts and leases. So like I said earlier, every node is executing the same distributed algorithm. There's no central coordinate saying, okay, now you repair, now you repair. Every node is saying, is it my turn to repair? And if it is, then they proceed with repair. And as part of this, they have to they have to be able to tell if the previous one got stuck. So like for whatever reason, maybe the previous node died, or maybe Cassandra is, has a stuck repair on that node. And so we built in this notion of heartbeats and leases. So at every stage of the distributed algorithm, the node that is currently doing something to the cluster is heartbeating to let the rest of the nodes know that it's still alive. It's basically saying, hey guys, I'm still repairing, I'm still repairing, I'm still repairing. And if you don't hear anything from them after 30 minutes, or some arbitrary timeout, then you actually kind of kill that work, you throw it away, and you keep moving. And this is actually really important because when you have thousands of nodes and hundreds of clusters, something's going to get stuck somewhere. You don't want the whole data set to be inconsistent because one node couldn't finish repair. On the reliability side, we had to kind of mitigate some of those issues with the tuning of Cassandra. And the way that we chose to do that was by making the work small, and therefore we could throw it away if we needed to. So no more 12-hour repairs, no more 24-hour full-range repairs. You'd always be running sub-range. We actually took this from the DSE repair service, kind of inspired. But what we kind of added to that was fine-tuning the ranges per table. So there's not like one split range. You don't say like, okay, split the tables into 4 pieces. Per table, for example, a table that might have 100 million or even 1 billion partitions is going to need a different partitioning scheme than one that has 1,000. So that was really important for reliability. But that also contributes to efficiency because it means that no matter how big your data set is, you can do about the same amount of work at a time. The repairs that have more data just take longer. It's not like they're more dangerous. And it also mitigates the overstreaming, understreaming issue because we picked that sub-range intelligently. In terms of scalability, because it was a shared nothing architecture, we kind of got this for free. So as we add more Cassandra nodes, they repair themselves. We don't have any kind of like n/1 scaling issues because every new cluster we add brings new repair capacity. Awesome. So let's actually walk you guys through a little bit of a repair that's actually running right now on a Cass Meetup cluster. So I think walking through this will kind of help you guys understand the data model, kind of how the repair service is coordinating. So at the top level, we have this notion of like a run, which you can think of as an end-to-end repair of a cluster data set. And this is really the only point where our nodes actually coordinate. So they do a lightweight transaction in Cassandra on this table, essentially. One node is able to create the repair run. And you can see here that a node has created repair run 9, which is 33% done. You can actually then dive in and see the sequence. So once that node grabs that lock, or sorry, not a lock, once he does the lightweight transaction, creates that row, now he's responsible for populating the repair sequence. So you can see here that it's populated a very predictable sequence, just sorted by the token. And then now every node is polling this table saying, hey, is it my turn? So for example, right now, this node is running the same algorithm that this node is running, but this one is the only one that's seeing the answer of like, yes, I'm the one that should be doing repair. And then you can dive in even deeper and see kind of the status of the repairs on that node. So we're kind of lucky that this cluster happens to be repairing right now, but we can see that we have the sample key space, which has no data in it, repaired extremely quickly, and just did 1 range. But this key space, the test1 key space, which has a little more data, has actually had to split up its data into many sub-ranges. And we can see that right now it's doing 4 in parallel, and it's kind of a queued system. So like as repair is complete, it's automatically kicking off the next one. this is extremely useful not only from the point of view of your Cassandra clusters getting repaired, but this data allows you to gain introspection into when the data was repaired. So for example, if you have an app team saying like, hey, did we have data resurrection last Monday? We can be like, no, that node that holds the data got repaired on the Friday. So we can guarantee you that you're not facing data resurrection, or you're not facing partially applied writes from that time. Afterwards, maybe. So that's kind of a high-level overview. I also think that I just want to demo real quick that we can configure all of this through this. I mean, we already kind of briefly touched on this, but I think this is amazing because it means that we can fine-tune the repair strategies for each use case. And kind of going forward, the repair service is already auto-picking some of these configuration options. We'd like to, kind of get it to the point where it's picking all of them. But then you can take this even a step further, and you can actually create kind of global views of your repair process. So this is kind of a mocked up names replaced to protect the innocent mocked up cluster view. But these are actually real production clusters, like they represent real production clusters. And you can kind of at a glance see, okay, which clusters have finished repair within their GC grace, or within 10 days, which clusters are taking a little longer than 10 days. This way we as an operations team and a development team can kind of work together to make sure that the clusters that take a long time to repair have a sufficiently long GC grace. That's also something that we actually, as we integrate into Cassandra, hope that we can automatically change GC grace based on repair status. So that way we don't have data resurrection automatically. So the colors here, just real quick, are green means that it's good, blue means that it's running, orange means that it's been running a long time, and dark blue means that it's running post-repair hooks. So that's kind of the final feature set of repair set, of the repair service, is that after a repair finishes on all neighbors, we can actually run configurable hooks. So for example, if you want to run full compaction on your size tiered tables after you've finished repair, you can do that. Or I guess more realistically, maybe you'd want to run cleanup to clean up any data that node no longer owns after the repair process. But that's all something that can be extended as the user needs. Yeah, so that's like the demo. Let's just go back to this since we did a demo. Yeah, it's also worth noting that in terms of on-call load, this self-healing system has brought CDE on-call pages down 50%. So half of all of our on-call incidents were repair-related. They're no longer happening because this is preparing all of our data for us. All right, so that's all like really nice for Netflix, but we think that the next logical step is contributing this back to the community. So right now, the way we've implemented this is that repair service is a sidecar that talks to Cassandra over JMX and stores the data in Cassandra itself. We'd really like to move towards it being in Cassandra itself. We think that the design is fundamentally compatible, and we'll be working with the community in coming months to make that happen. Just to kind of give you guys a taste of what that might look like, you can imagine an option on a table, just like compaction. So you say, with this table, I'd like repair to happen, I'd like full repair to happen with a minimum wait time of 24 hours. So it's not saying schedule it Tuesday at 2, it's saying run it continuously, but wait 24 hours between repairs. Or you could pick whatever interval makes sense for your repair rate. Or you could actually interrogate the database. So how many of you guys run repairs in Cassandra? Okay, how many of you guys know how many of your nodes have repaired at any given time? Apple guys, all right. It's kind of tricky, but we think that with this kind of state that's been coordinated through the repair service, you could just run a simple node tool command, like, hey, 23 out of 288 nodes have been repaired, and we estimate that this repair will finish before GC grace. It gives you additional context that could help you, for example, debug, which node is repairing right now, maybe which other nodes is that repair impacting. But I think kind of more interestingly, it could also tell you when something is going horribly wrong. So for example here, we're not going to finish repairing our critical business data and very important key space before GC grace, which is clearly very critical and bad. So we think that surfacing that kind of information to developers and operators is kind of the next step. Yeah, so I guess the takeaway I hope from this talk was, let's kind of move Cassandra from hopefully eventually consistent to actually eventually consistent using kind of auto-scheduled repair. Thanks, guys.
Now the EV Cache team will tell you all about EV Cache.
Thanks, Joey. Thanks, Joey. Good evening. Now we'll switch the gears from persistence to caching. So on a busy day, you go home, you relax, and you decide to watch Netflix. You log in, you pick a profile, you get to your personalized homepage, you click on a video that you have been watching the day before, or scroll down and pick a new video that's been recommended for you. Or you go back and change your profile, go to a new personalized homepage for that profile, and click a video and continue watching. So during this experience, or during these interactions, personalized Netflix experience, there are several customer requests have been served from the several different AWS regions. Netflix operates on 3 AWS regions: US East, EU West 1, and US West 2. So your request can be served from any of the 3 AWS regions. A few years ago, Netflix moved from an island model to a global services model. What that means, we need to have the data in all 3 different regions. Providing globally replicated data reliably at a speed of RAM for a caching systems at a global scale is a challenge. Today, I'm going to talk about the cross-region replication system that we have built to replicate the data for a caching systems, caching service we built here at Netflix called EV Cache. My name is Sridhar Enugula. I'm a senior software engineer on the EV Cache team. Before I jump into cross-region replication, I want to talk about a few use cases of why we use caches. We use caches for predictable response times, typically under sub-milliseconds. We use caches to reduce server costs. You might have heard a lot about microservices from Netflix. If you haven't, we have lots of microservices. So most of these microservices auto-scale. That means they maintain their state either in cache or persistent store. In this case, Cassandra or EV Cache. So when a request comes in, most of the times these requests hit the cache. Our cache hit rates are pretty high. So and we serve the data to the customer from the cache. That means the requests are not going to the server. So the server farms can be less, so that reduces the cost of the server, the farm, so that reduces cost in turn. We also serve fallbacks out of EV Cache. So when a microservices is experiencing a problem, and if we have to, instead of blowing up the service, we serve fallbacks until we fix the problem. So these fallbacks are served out of EV Cache. We also share data between the microservices from caches. So what is EV Cache? It's ephemeral volatile cache. It's a distributed key value store, highly resilient to the failures. It's built on top of Memcached. It's tunable within a single AWS region and also cross-region. We use caches widely at Netflix. We use, in a personalized Netflix experience, we touch tons of caches. So when you log in, or when you sign up, we touch caches. When you log in, when you choose a profile, when you're scrolling through the home page, or when you get to your home page, at any given time you are in a dozen or more A/B tests. So we touch caches for the personalized experience, and we touch lots of caches. And all these caches need to be replicated to all 3 regions of AWS because of our global service model. Just to give you a sense of scale for the replication, we replicate hundreds of EV Cache clusters. We replicate the data to all 3 AWS regions. And we replicate millions of replication events per second. We replicate tens of gigabytes of data per second. Why do we need to replicate? So we talked about requests can land in any AWS region. Let's look at a few more use cases. Why do we need to replicate? One of the use cases is our pre-compute algorithms run in one of the AWS regions. And they run in an AWS region wherever the compute capacity is available. So we need to replicate the data Like for example, if a home page can be generated in EU West 1, so we need to replicate the data, the generated data to EU West and US West 2, so that if we need to move the traffic, or if your request lands in the other region, you will be served, or you will have a seamless experience. I was telling about, we have lots of microservices, and we deploy code every day. We make lots of production changes. We make hundreds of production changes. So failures are inevitable. Anything could happen. So our disaster strategy is to move the traffic from the area, from the region we are having problems to the other two regions. So our traffic team, if it happened to happen in the night, our traffic team moves the traffic from, in this case, from US West 2 to US East 1 and EU West 1. Because we have already replicated the data, the user will have a seamless experience. Let's take a look at this. So when we move the traffic from US West 2 to US East 1, and we move the traffic from US West 2 to part of the traffic to US East 1 and part of the traffic to EU West 1. So the users will be served from US East 1 or EU West 1, and they'll have a seamless experience because the data is already available. Now let's look at how we replicate. Consider we have an application in region A, and we have an application in region B, and they are talking to the same cache. So in reality, we have three regions. Just for the simplicity, I'm demonstrating here with the two regions. If we write a mutation, application A is writing a mutation to EV cache in region A. We write the data about the metadata about the mutation itself to a Kafka topic in that region. And we have an application called replication relay, which reads the Kafka stream and potentially read the data from the EV cache in that local region and post the data through a HTTPS link to another application called replication proxy in the other region. And replication proxy in the other region, on behalf of application in region A, writes to the EV cache in region B. When the request goes to region B, my application in region B, in this case, a traffic failover scenario or a disaster scenario, the data is available for the customer in region B, and it goes the same way when the application in region B writes, it goes the same way, and it happens three ways. Basically, it's 6 ways it happens. So we replicate the data around all the three AWS regions. So one thing is not mentioned in here, in this picture, is SQS. So we actually, for a failure scenarios, what if something goes wrong, or we are not able to send the data over there? We also write, when in a failure disaster scenario, in a failure scenario, we write to SQS, and there is another application which is processing. But we hardly see that happening. Most of the times, this is pretty much reliable, and this works very well for us. So that's all I have for today for the cross-region replication. So Shashi will talk in detail about EV cache server architecture and several use cases of EV cache itself. Thank you.
Thank you, Sridhar. Today I'm going to talk about EV cache, how we, the evolution of EV cache from being an in-memory data store to a data store which uses both in-memory as well as SSD. EV cache, as you know, is a distributed key value store that uses memcached to store its data. So the architecture of EV cache basically consists of two components, an EV cache server component and an EV cache client component. For today's talk, I'm going to mostly concentrate on the server component. The server itself consists of a memcached and a sidecar that we call it EVCAR. Memcached holds all the data that's needed for caching, and EVCAR mainly is used for administrative and any monitoring purposes. So whenever the server starts up, the EVCAR registers itself with Eureka, our service discovery. And whenever a microservice needs to talk to a server, the EV cache client directly bootstraps that information from Eureka and connects to the memcached directly. After this, any communication that needs to happen between microservice and the cache is directly between EV cache client and memcached. So when the microservice needs to fetch any data, it asks EV cache client to fetch the data, and EV cache client performs that operation on it. Now, what are some of the use cases of EV cache at Netflix? We use EV cache for look-aside caches, EV cache as a transient data store, and primarily as a data store itself. So let's look at in detail what each of these use cases mean. So for look-aside caches, EV cache fronts the data in a persistent store, for example, Cassandra here. Now, when the application needs to look for any data, first it calls the EV cache client. EV cache client checks if the data is present in EV cache. If it is present, it just returns it. If not, then the application calls the service which fetches the data from the persistent store, and then the service puts it back to EV cache client so that any subsequent requests for that particular data can be directly fetched from the cache. So the second use case is caching as a transient data store. For example, let's take a viewing session. So whenever you click on a play, so you want to watch a video and you click on the play, we create a session. So an application gets this information and it creates a session in cache. So as you keep watching the movie, we are continuously collecting the data and the session information is being continuously updated. This can be done by one or other applications. So the details about your viewing session is continuously being updated. Finally, once you're done watching the movie, we roll up the data and it's being stored. So the same piece of data is being manipulated by multiple applications here. Finally, another use case is EV cache itself as a data store where the data is not stored anywhere other than EV cache. This is primarily used in a lot of our pre-compute systems. For all the hundreds of millions of users and the profiles, we compute the recommendations, their home pages every day, and that data is directly stored in EV cache. So that any time you visit the website or using your device, the data can be fetched directly by the online application and then presented to you. So the whole picture looks like this. And since we do a lot of computations, this data that we need to store can be pretty huge. When we started EV cache, it was, now we term it as EV cache classic, all the data was stored in memory. So that means the cluster sizes were pretty large if you wanted to store millions and millions of users of data, right? So which meant this could become very expensive, right? So also when we have multiple regions, we need to replicate all this data from all the regions to everywhere. So that means your data has now suddenly increased by a factor of 3, which is even more expensive, right? So what can we do about it, right? So that's where we started experimenting with, can we use SSD to store some of this data? So one thing that we noticed during with the global replication strategy or global Netflix strategy is most of the users are sticky to a particular region. For example, let's take all of us here, right? When we go to Netflix, we usually end up in US West 2. We very rarely go to US East 1 or EU West 1. So we go if we do migrate the traffic or if you are traveling. So that means most of our data the amount of the data that we need to store in RAM is just a third of what is needed. So that means we can store a part of the data in SSD and the more actively used data can be stored in RAM. So with this strategy, we can also reduce the cluster sizes, which means our deployments are much quicker, which is also very cost efficient. How we went about doing this is through a project called as Moneta. So when we started the Moneta project, we used RocksDB to store the data on SSD and Memcached to store the data in RAM. It still looks like Memcached, it talks the Memcached protocol. So whenever a request comes to mnemonic, which is a process that mediates between Memcached and RocksDB, it takes the request, first it checks if the data exists in Memcached. If it doesn't exist, it calls RocksDB, reads the data from Rocks. If needed, we store it in Memcached and return the data. So this worked very well for EV cache as a primary data store. When you're computing the data overnight and writing, it worked very well. This did not work as expected for the use cases where EV cache is used as a transient data store or as a look-aside cache. So when we're trying to work on those issues, Memcached released a feature called as Memcached Flash, where the data is transparently stored in RAM and on disk. So in this case, the metadata about the data is stored in RAM, and the actual data is stored on disk. So whenever you need the data, we quickly check if the data exists on the SSD, and from the SSD we know where the data is on the RAM. We check the data if the key exists in the RAM. And part of the metadata also contains the location of the data on the disk. So we go to SSD and fetch the data and return it. Now, since every request hits SSD, there may be some latencies or some performance issues reading the data, right? But in reality, we didn't really see that. This is a distribution of the read requests on a particular host. If you look at it, most of our requests are served within 100 microseconds. And this is well within our SLA. So now let's take a use case where we want to store a terabyte of storage. So if you want to store it in an EV Cache Classic, which is a RAM-based caching, you end up with requiring 20 R4 2 extra larges. Whereas if you want to store this data in the Memcached Flash, all you need is just one i3 extra large. So that was huge cost savings for us, right? So, but what is the catch here, right? The catch here is the network bandwidth that we can expect out of a 20 R4 2 extra large is 40 gigabits per second. Whereas with one i3 extra large, you'll get roughly 2.5 gigabits per second. So if you are network bound, you may need a few more instances to support the network capacity. So that's about it. Thanks, Yanis. Yeah. Okay.
Thank you, Sasi, and hello to everybody. My name is Yanis Papanagiotou, and guess what I do? I work for cloud database engineering. Half of the people I also work for that team. So today I'm going to talk about graph databases. So recently we've seen an escalation of use cases inside Netflix, I'm assuming in other companies as well, where these use cases have a lot of graph semantics, and they need more complicated data structures to represent their data models. So when we started thinking about this problem, we saw whether we can use, for example, a relational database. And the problem with relational database is when you have joins and when you have foreign keys, the performance gets degraded. Whereas with a graph database, it's more natural for a human being to represent the data in the framework they want it, but as well as the graph database can be more performant for graph and complicated data models. So one-to-many relationships can be easily used inside an SQL framework, but many-to-many relationships, you usually need some sort of a graph database to capture those. And then it was about October when the CDE team decided to start thinking about offering this as a library inside Netflix. And we had an option about November when the AWS conference happened, is to either move forward with AWS Neptune, which is a managed service, works really great, or versus using an open source project and Cassandra. And given the great work that Joy and Vinay has done on the repair service, and we get so excited to say, why don't we actually use this work? So what we did is we integrated Janus Graph with Cassandra and Elasticsearch. The integration is already open source available, but we did the hooks inside Netflix and we made it work for us. So a Janus Graph, in summary, is a highly scalable graph database which is able to store fairly advanced graphs, and you can query that. And it's highly performant. It's highly performant in our case because it uses Cassandra at the backend, which is you can scale Cassandra the writes, you can also scale the reads. As many nodes as you add, you can scale linearly. It also supports thousands of concurrent users, and you can do fairly advanced queries in a graph framework. One great advantage about Janus Graph is its ability to be able to use Tinkerpop, a Gremlin graph query language. The advantage of using Gremlin is, for example, if you're using now one use case that you want to migrate it to Neptune, that's okay. If you want to migrate to Neo4j, all of these graph databases, they support Gremlin. So for us, the migration from one framework to another framework to another framework would be very, very easy. So Janus Graph actually offers that. At the same time, it supports Cassandra, it supports HBase, Berkeley DB, and a few other data and Bigtable. But for us, we have great experience on Cassandra, we have a great team in Cassandra, so we thought of integrating with Cassandra specifically. So a few things we did internally in Janus Graph, and it may be some good ideas if you plan to use Janus Graph, is some of these. So one thing we want from our users is to be able to actually, when they connect to a Cassandra cluster, to actually use the name itself, like a string of the name of the Cassandra cluster. So we didn't want to go like change the IP addresses or change the host names. So for that, we integrated with Discovery, our own Discovery service, which is called Eureka. So every time, for example, you want to open a connection from Janus Graph to Cassandra, you just add the name of the Cassandra cluster. The second thing we did is we integrated with dynamic fast properties, which is a framework that we have inside Netflix, which is called Akeos. It's also open source as well as Eureka. And so if somebody wants to change a property in Janus Graph framework, they can just do that in a UI, or they can just do that programmatically through Akeos. The third is we integrated metrics. So for example, Janus Graph itself, it doesn't provide enough statistics for us. So what we did is we integrated metrics and Spectator, which is another open source project, which actually captures statistics for us. So we were able to see how many queries we do, what are the latencies, and therefore debug if there are any issues when something happens or for example, in complicated graph queries. The fourth thing is request tracing. For example, when we want to figure out which services or microservices are dependent to which other microservices and what are the graph queries they do, we can do that by using Visual and through a software which have open source, also called Salt. Rup in the beginning showed the view of the graph of Visual itself. The fifth thing is that inside Elasticsearch, we are very proponents of chaos engineering and producing failures in order to determine if our services can work under failures. And therefore, we wanted to integrate that inside the Janus Graph domain. And that's why we integrated with failure injection testing fit. The sixth is we want to make sure our assets are secure enough. And therefore, we integrate with our own credential management framework, which is called Metatron. Now I'm going to go over a few use cases that we have used Janus Graph. One of the use cases is digital asset management. So think about when a movie goes from the cloud, from the studios to the cloud, we have to take that movie and we have to decompose it in the assets. So an asset itself can be, for example, the artwork, and that artwork can contain a character or a person. For example, I think last week we released Jessica Jones #2, and who knows who's the actor in Jessica Jones? Kristen, great. So in that case, Kristen would have been the person, and the character would have been Jessica Jones. So, for example, an artwork also may contain a few images in different formats, like WebP, PNG, or JPEG. And the movie itself can also contain a different display sets. For example, if you want to have different languages, like English or German, as Vinay said before, and this will be represented inside the display set. And again, display set can have different audio tracks. So if you start thinking about this use case, all this can be modeled with a graph in a graph framework in the graph database. So in more details, the DAM, which is the digital asset management, effectively all entities are vertexes. We have collections, which are also vertices. And the relationships are the edges in the graph framework. Indexes can have composite for property key-based lookups. And we also want to search DAM externally by doing text searching, and that's why we can do that using Elasticsearch and outside of the Janus Graph context. A few statistics of how big is DAM right now. We're talking about 200 million nodes in production, about 200 million sources in test. There are more than 10 different microservices that are actually querying DAM to get information about the movies and the artworks, etc. And 70 asset types and hundreds of queries and updates happen per minute in that service. But apart from DAM, we also have a number of other use cases. One of them is authorization, user, and partner management. So think about how we have, when we want somebody to partner with Netflix, then we have relationships that are being established. These relationships can be complicated. For example, we can have a Gmail account for that person, or an asset internally Netflix can have a Gmail account, and he may have a white page entry, or different types of entities may exist for a person or an entity. And therefore, this can be a perfect use case to store in a graph framework. Distributed tracing. So before I said that we integrate that inside Janus Graph, but SALP itself can also use a graph framework. If you think about microservices, how they connect to each other, and the way we can actually trace the connection between the microservices, this is if you open that up, it's actually a graph. Third is network dependencies. So when an incident happens and we have to fail over from one region to another region, we always want to go deep and find out why this incident actually happened and which service is responsible for that. So if you think about all these services being related to each other, we want to have graph framework to query and say, oh, which actually service died and which services are dependent to this one. Therefore, what is the failure domain? And we can do that in a graph framework. Last but not least is the way we map Netflix infrastructure relationships. For example, how the code gets committed on STAS, how the jobs are being built on Jenkins, and how it's being deployed on Spinnaker. So these are the use cases that either use a graphs, Janus graph, or are potentially use cases that can benefit from a Janus graph context. And that's all from me.
Anyone has any questions? Yeah.
So you're a big user of AWS. So what is the exit strategy? Like tomorrow, like AWS is too costly for user of Netflix. What is the exit strategy?
Sure. So the question is, we are a big user of AWS, and what is our exit strategy if there is something?
Yeah.
No, absolutely. So we keep, we value our engagement with AWS very much. They have been a great partner as we have migrated from data center to cloud over all these years, and continue pushing features and making their cloud enhancements very well. So for now, and it is something we keep thinking, but it's not something which it's not something we need to worry about as such, because I think we believe in that partnership quite a lot, and it's working very well for us. Any other questions? Yes.
When you mentioned that Janus Graph would support special types of queries, and you gave some examples in the end where you were using it, it's hard for me to make this mapping. Like, what kind of queries are these that you can easily express with Janus Graph, which you would not be able to do with other storage?
That's a good question. So,
Yanni, can you repeat the question, please?
Yes. So I think the question is, in all these use cases that we saw in the end, what are the types of queries that cannot be served by things outside of the graph context, if I get correctly right?
No, I mean, what's special about the graph context that makes it so beneficial in this case?
Right.
What kind of queries, yeah?
So it's more natural to depict a use case when you see being a graph to a graph query than trying to make that a complicated query in an SQL domain, right? So as I said in the beginning, when you have, for example, a complicated join with foreign keys, then the performance may be degraded. So that's when performance is important. Graphs tend to be faster in that case. So if you have things that you want to traverse inside the graph in multi-levels, then graph is actually better in order to when they do the memory management of the graph itself. So the third thing is that it becomes more natural for a human being to represent this in a graph query rather than, for example, a select query, right? So that's a few advantages that we use the graph.
I have a question. So is the Data Explorer open source, or are you guys going to open source that?
Very good question. So the question is the Data Explorer open sourced, or if not, when are we planning to?
Yeah, so it's actually not open source at the moment, mostly just because of other business priorities. But I'm curious, can I get a show of hands of who would use it if it was available?
Pretty good.
Well, that's good. That's good. So there's interest there. So it was designed to be open source. So sort of where we have sort of seams where we interact with Netflix's ecosystem, there are seams there. So the framework's been laid, but it's just we don't have a firm date yet. So keep coming to the meetups and stay in touch.
We will open source. We believe big in open source. And
Another quick question. So I know you guys used TitanDB before for Graph. Why are you guys still using that, or why do you do the switch?
Right. The compare. So Janus Graph is the code base of Janus Graph is effectively the code base of TitanDB. So TitanDB, I think they stopped committing the code, and effectively at some point, I think Google took over the project and changed the names and converted to a Janus Graph under a different license. So effectively, Janus Graph is the evolution of TitanDB. So if you guys are using TitanDB, you better move to Janus Graph.
Yeah.
Since there are so many moving parts, whenever there's an outage in the AWS side, how much work is involved to move data around to make it highly available?
Sure. So the question is, since there are so many moving parts, whenever there's an outage in AWS, how many moving parts are there to move the data around, right? Is that the question?
Yeah, how much effort is involved?
Sure, sure. So to give you a quick answer, it is under 7-8 minutes. So our traffic team does an amazing job. So Cassandra, as we said, right, we are deployed in 3 regions. And all 3 regions are taking traffic from everywhere, and the data is being replicated across all the 3 regions. So whenever there's a problem in one region, the traffic team seamlessly shifts the traffic to the other 2 regions. And we do all these mock exercises we call Chaos Kong, where we evacuate a region. And Sridhar was showing you the slide where one region was evacuated and the traffic moved to the other 2 regions. So that happens very seamlessly and under 7 minutes. So there's not a lot of disruption. And we keep doing that exercise quite often to exercise the muscle that we are able to recover. Does that answer your question?
Sure, yeah. And it's all automated or sort of automated?
Yeah, it's pretty much automated. And we do these on such a regular basis that, yeah, it's become a normal process. Yes.
I'm just curious, the data that is in the graph database now, was it in Cassandra before or in a SQL database before? And what was that process of like migrating it into a graph database?
The question is, the data which was in graph database now, was it in SQL database before? And if it was, what was the process of migrating?
Right. So Janus Graph is not a database itself. Janus Graph is more like an API layer. The data are being stored in Cassandra in a binary format, but they're still stored in Cassandra, right? So there was no question between moving the data out of Cassandra to Janus Graph. It was already, it's still in Cassandra, right? Yeah. And the indexes are in Elasticsearch, so we can query them. So that's the advantage of Janus Graph, that you can use these databases in order to query the data.
Very cool.
Most of the use cases, when they started thinking, I think the first one was digital asset management, still the biggest one. They started with TitanDB. And effectively, at some point, going back to the question that you asked, is we decided to start moving to Janus Graph as this is the maintained. We start committing code. The other advantage of Janus Graph over TitanDB is that it supports the Cassandra query language, whereas TitanDB used to support an older driver actually developed inside Netflix called Astyanax. So it still uses Cassandra semantics, but it stores the data in a graph format.
Okay. Thank you.
Yes.
Yeah, how do you identify like bad actors who is like using Cassandra, like somebody is writing large partitions or like doing funky queries? So how do you identify and then stop them? And
Sure. So the question is, how do we identify rogue apps or rogue queries in Cassandra? Vinay, do you want to take it?
Yeah. So right now, the way we do it through all the metrics that we monitor on both client side and server side. So on client side, even in Astyanax and the Java driver, we integrated metrics to see the number of bytes coming in, number of bytes going on. So that identifies potentially a bad user querying a lot of data, or select star or bad queries. And that way we are also planning to work on, there are open data as well to block some bad queries as well. So that would be the future, but right now it's all through metrics and other things.
so then you kind of like manually work with them and then tell them to stop it, or like when there is an outage, then now what you do?
Right now it is it creates alerts and triggers those alerts, and we engage the customer and work with them.
So if there's a bad push or something, so people have to do the rollback, or yeah, but it's hard. Yeah, François.
I have a question with respect to the caching. Why did you not opt for a more simple invalidation pipeline versus a push, as I understand, where you're actually pushing the new mutation? And isn't there possible inconsistencies? I don't know, when you're pushing to your queue versus to your main storage, your ground truth.
Can you repeat the question, Shashi?
Yeah. So basically, your question is, why do we choose to, how do we handle inconsistency in data when we do cross-region replication or within the.
Well, why do you need a replication to start with versus just invalidating across regions?
So yeah, across region, it's a tunable replication strategies. So if it's typically data fronting and persistence to data store like Cassandra or something, what we do is a write, we do a delete in the other region. So to keep the caches coherent, it's all tunable. So or we do full replication. Sometimes when we migrate the traffic or when there is a high cache miss rate, the services are under a lot of pressure. The way a cache can scale, a service cannot scale that way. So in those cases, what we do is we do full replication. And we make sure the data is coherent, we check it. So as Sridhar mentioned in his talk, we use both Kafka as well as SQS. The Kafka path is for speed and SQS path is for consistency or reliability.
Yeah. But if the app fails, like before it goes into Kafka, it also can't publish to SQS, and you have like the potential for inconsistencies between regions. Like, do you attempt to deal that, or is that just something you acknowledge might happen?
Yes, good question. So when we write the mutation, effectively at the same time, the event for Kafka is also written. So effectively, all the writes happen at almost the same time. Yes, there is a possibility that before processing that event, your instance can fall. In those cases, the data can be inconsistent. But we also, assuming if that doesn't happen, if the write to Kafka fails, we always write to SQS.
Have you looked at some trigger or some ways to basically tail a commit log or something to basically be sure that you're following the ground truth?
So we do the replication from the client side, not on the EV cache server.
Okay.
So unfortunately, there is no lock to tail. So we can go from the server side also, but it's based because each server is independent of each other, right? So the client basically sends the event before.
Yeah, Jay.
Follow-up question. Is it possible that the data is in Kafka but not in SQS yet?
The question is it possible that the data is in Kafka but not in SQS? Yes, for EV?
So it's either or. Basically, it can either be in Kafka or in SQS. So write to Kafka fails, or then we write to SQS. But you can also have duplicate records. So you end up sending duplicate messages. So if you write the same key with the same value twice.
Are you using containers for the since we're using a lot of microservices? Are we using containers? If containers, what are we using for the architecture, like Kubernetes, or those kind of things?
Sure. So the question is, are we using containers because we are using a lot of microservices, and if we are using, are we using Kubernetes? So we are using containers. We have a special team called Titus team. They manage the containers, and as far as I know, they don't use Kubernetes. They have something inbuilt. Does anybody have insights into our?
So they schedule a framework called Titus, and I think they plan to open source it sometime.
Yeah. So underneath, I think they're using. Kunal, do you want to?
Yeah, I believe it's using like Docker and Mesos.
Yeah, Docker and Mesos.
So actually for that question and a few other questions you were asking about failover, the Netflix tech blog, which you can access from techblog.netflix.com, actually has a lot of postings about things like that. I believe Titus did something there a few months ago, and I think there was something called Project Nimble, which is the 7-minute failover Rupa mentioned. I think they just did a little paper on that there just a few weeks ago, I think. So yeah, a lot of these questions, you can go in there and actually see a lot of information from the teams that actually develop those systems.
Okay.
And it could be a very good entry point.
So techblog.netflix.com, it has a lot of articles and insights into how different teams are solving different challenges and problems. Yeah.
So, and there's been a lot of projects that are motivated by developer velocity. I'm curious if those projects, following up on those projects, you have seen increase in terms of quantity of data models or clusters created. And if this, with an increase in quantity, you have seen a decrease in quality. What is the review process that's being that's imposed, etc.?
So the question is, since we have so many systems and so many different types of data models which can be created, and what is the review process to keep it tapered, right? Like, is that the?
It's easier to create.
Yeah.
Or are they of high quality?
It's easier to create and are of the high quality. Is that the question?
Yes. If everybody starts creating a lot of quick schemas or whatever.
Sure. So absolutely. So of course, the self and in Netflix we have a culture of freedom and responsibility, right? So that is very valued. So people are welcome to create clusters and create schemas. The assumption is, of course, they understand what they are doing, and we have a great team they interact with. So if they don't understand what is involved, if the complicated schema is able to scale at Cassandra, or is Cassandra even a right choice, right? So they do engage with our team who knows about all these polyglot persistence, and they can support them and tell them, hey, this will work or this will not work. So that engagement does happen. And we have seen for most of the production cases wherever there is an engagement, that is a very successful model because there are less production problems, or people are not, they don't have surprises in production for their use cases. So in Netflix, people engage with CDE team. And the different type of data models, it's not been a problem, especially because I think that training, we try to do a lot of user interactions and training. We have internal CDEUs created where we coach the teams in using these technologies.
And also we try to put a lot of best practices in the tools itself, and won't let them commit those mistakes easily. But there could be scenarios where everyone has access to everything, but that is where we go behind and catch.
Yeah, like for instance, like the tool that Gim was showing, the Data Explorer, like we're building some of those guardrails and best practices sort of in the tool itself. In the Elasticsearch sort of self-service aspect, we're kind of like helping guide people towards having appropriate retention policies so they don't like grow their cluster indefinitely and things like that. So they also get like email notifications when they're like running idle clusters and things like that. So there's a lot of that information being provided to users.
How large is the CDE team at Netflix? How large is the team?
Okay, so the question is, how large is the CDE team? I think we are 22 total.
So on the data model part of it, so when someone is creating a model, is it thinking more on read optimized side of it, or does the team get in and make it match it or make it work?
So the question is, when we are trying to create a data model, is it more tuned towards the read optimized, or the team work on both read and write? Does anybody want to take?
Yeah. So most of the data models, depends on the use cases, but most of our use cases are 80% reads and 20% writes. So we have more read-heavy clusters. But if there are some new use cases where they have a write-heavy use cases, they work with us, and that is when we help them choosing the right database, be it Cassandra or Elasticsearch or EVCache. And that's where the engagement comes in. But if they know what they are doing in terms of this is a standard way to do it, then these self-service tools will help.
Sure.
Go ahead.
On the GraphDB side, have you looked at the DataStax GraphDB, or any thoughts on that?
Sure. So the question is, on the GraphDB side, have we looked into the DataStax GraphDB, and any thoughts on that?
Right. So that's a good question. One of the reasons we chose Janus Graph is because of the open source side of it, and because it gives us the ability, whenever there is an issue, we can inside and file PRs. I think a few of our engineers have already filed PRs for Janus Graph to fix a few issues that we've seen over in production. So that's why we have preferred more like an open source solution versus a proprietary solution.
So for the Cassandra, like you guys, how you guys do the capacity planning? So is it like customer telling you like they know they need like 10 node cluster, or you guys like have some formula?
Sure. So the question is on Cassandra side, how do we do the capacity planning? Is the customer telling us how many nodes, or do we do it? So no, our team does the capacity planning, and there was a talk at Cassandra Summit last time where I think Ajay had a detailed talk on how do we do capacity planning. So, but the idea is you interact with the customers, get to know the read ops, our write ops, and we take care of spinning the cluster, but the long-term goal is to make it part of self-service, where the user doesn't need to know everything about Cassandra, but they can just put what is the data size, how many read ops, what is the SLA they require, right? Like what is the 99th, 95th, and average latencies, and based on those numbers, we can create the cluster for them. Anybody?
And also we built predictive systems to see the predictions of the data usage going in the Cassandra and stuff. The plan is to integrate that as part of CDE service, so everything is self-service there. But yeah, it's a mixture of engagement and tools that involves capacity planning.
Any other questions?
So will it cause lots of small Cassandra clusters instead of bigger ones, bigger shared Cassandra clusters?
The question is, do we create multiple small Cassandra clusters instead of bigger ones? Joey, you want to take it?
Sure. Yeah, generally we opt towards more like kind of one cluster per microservice. There are some shared clusters, especially some of like the general purpose, test it out, try it out kind of clusters. But generally we try to keep it 1-to-1 or at most like 1-to-3. We find that makes it much more robust because you can very quickly isolate what's actually causing a performance degradation, as opposed to on multi-tenant clusters. It can be extremely difficult to kind of figure out which tenant. And given that we're in a cloud environment, it's really very easy to shard on cluster because you can just, instead of spinning up 20 machines in the general cluster, you can spin up like 5, and then 5, and then 5.
And also in terms of the size of the cluster, it depends on the microservice. If that microservice demands lot of read ops and write ops, that is a cluster that keeps growing. But the smaller clusters would.
So is there? Yeah.
Yeah. So are you using like multiple, different AWS instance type, or like?
The question is, are we using multiple or different AWS instance types?
So for persistent store, we are majorly in the I2 family, and for caching,
Caching we use I3, SARFO.
What about for Cassandra? Do you use?
Cassandra, we use I2s because they are SSD based, most of them, but we also have, I think, D2s for.
And I3s.
And
I3s,
I3s
D2s,
also, yes.
D2s. And then
So what is the typical bottleneck? Like is storage bound or CPU bound? Or?
What is the typical bottleneck?
I don't think there is a typical bottleneck. We have lots, like some use cases are CPU bound, some are cache bound, so like you need a very hot data set. Some are disk bound, they just have a lot of data. I wouldn't say that there is a typical.
Yeah, there's no general bottleneck.
Some are network bound.
Yeah, some are network bound.
Depending on the use case.
Everything.
Pretty much. Yeah, Francois.
So do you hit a situation where that the initial class size is not big enough? So as customer are using the database and they have more data, so how do you expand the cluster?
So the question is, if the initial cluster is not big enough and suddenly users push more data, how do we expand the cluster? Joe, you want to take?
Yeah. On the Cassandra side, we usually add the slots in middle, which is essentially doubling operation. So your 6-node cluster becomes 12-node cluster. Cache, do you guys do?
We typically go the way we need it. Yeah.
Like adding nodes.
Yeah, it's worth noting that every data store that we deploy is linearly scalable. So Elasticsearch, EV Cache, Cassandra, every one of them, you just add more nodes and you get more capacity. That's like a very core part of the CDE service.
How do you back up? Is that for the Cassandra cluster to S3 or something else? And do you have like a restore wonky or a similar type of chaos?
The question is, how do we back up, especially for Cassandra, and to S3, or what is the process, and how do we do the restores?
Yeah, so we back it up to S3, and Priyam is a sidecar which manages Cassandra backups. And restore we do every weekend during like Thursday, Friday, Saturday. We do the restores. So our backup is being checked almost every weekend. So worst case, you have last week backup if there's any corruption or something. But
it's worth knowing that the app teams actually use that in their, so in the testing environments, they use their production restore essentially, so that they get production level data.
And also for offline processing, we have Augustus, which is our open source product, which reads the SS tables from the backup and analyzes the data and puts it in Hive for analytical use cases. So backup integrity is checked almost like every minute as new file is being uploaded to S3.
Anshu?
So you have plenty of different clusters. They have each their own bottlenecks. How do you do capacity planning?
So it's, yeah, basically the capacity planning involves our predictive tooling, which predicts the usage of the cluster in next coming quarter or next 2 quarters. But also there's a lot of engagement involved, working with the customers, looking at how the usage is going to grow. But most of our data is backed by the EV cache, and EV cache scales pretty easily. So that way on Cassandra side, we have less pain that way.
If your question was aiming more at like what tools do you use to figure out what is the bottleneck, is that?
Well, so you have different hardware bottlenecks, and you need to cope in like what are the resources that you're limited on. So I'm thinking it could be quickly becoming hell of.
So we rely very heavily on a number of tools to figure out the bottlenecks. A lot of them are developed by Bern and Greg, actually, at Netflix. So for example, like we can use tools like the BCC tool suite, which can tell you things like how many of your reads are hitting your cache. So for example, we aim for like a 30 to 40% plus OS cache hit rate. You can use operating system metrics like CPU scheduling metrics to tell if adding additional cores would give you more speed. So for example, if you have free cores, then adding more cores doesn't solve a latency problem with CPU. So like we have a number of metrics, such as like disk latency, CPU scheduling latency. So CPU scheduling latency is like not how much time you spend executing on the CPU, it's how much time you spend waiting to execute on a CPU. And these plethora of metrics can pretty easily paint a picture of what you're limited on. And then you can just add more of that resource, typically by just adding more machines.
To add to Joyce's answer, for EV cache, what we do is we have set up alerts on how much free space we have, on how much network utilizations we do. So whenever we cross that threshold, we check it. If there is a scale up, we bring up either a bigger cluster size, warm up the caches, and then get rid of the old one. Do the typical red-black deployments.
So on the predictive tool, so the end result will be a number of nodes, instance type, JVM size, to that detail, or is it?
The predictive tool at the current stage is essentially tells you when this cluster will tip over the SLAs. That would be the first step as part of our input, and we take it from there. But we are working on making that predictive tool metrics as well.
But in addition, would you use some kind of a metrics, so like burn test using that load simulation and gather some data and kind of?
So the question is, do we use any simulations and try to see when the cluster will be running out of capacity, right? So basically, when we are dealing with capacity, we look at few things on different, like Joey mentioned and Vinay was mentioning, and even Shashi. So it depends on the cluster, the type of the cluster, the SLAs which have been promised, right? Like ultimately at the end of the day, the application which is interacting with Cassandra or whatever data store, if their latency requirements are not meeting, that means there is something wrong. Either they have changed their pattern or the cluster is running out of capacity, right? Or in terms of even disk. So there are a few things which we look at. And the predictive tool, which Vinay was alluding to, we do have some simulations where when there is a specific feature being rolled out, right? So the application team can say, hey, we are rolling this out. Can you let us know what is the headroom of your cluster? So in those scenarios, we do have like NDbench and tools like that, which can generate load, and we can figure out, is this cluster able to meet the SLA if we increase the cluster, the capacity, if we increase the throughput. Things like that. But other than that, we don't have, we are still building, we are still looking, because that is an interesting space we need to solve across all the technologies. When do we run out of capacity? The questions we are asking is, for a particular cluster, what is my headroom? And if I increase if I double my throughput, will this cluster sustain the SLAs? Or when it will be running out of disk?
I think I'd just like to add that NDbench is actually a very core part of this. NDbench is a tool that Vinay wrote and we open sourced, I think 2 years back, which allows you to fairly benchmark any cloud database. So Elasticsearch, Dynamite, Cassandra. And that's actually quite important for us to, for example, like validate, how many 4 kilobyte reads and writes can an i3 do versus an i2 do realistically before we start tipping over our 99th percentile, latency SLO. So, kind of, we can observe what's happening in production, but we can also try to simulate different workloads using NDbench, with multi-region clusters, so that we can actually see what the real latencies will be like. And I think that's before we try any new instance type, for example, we run it through a suite of NDbench tests, which simulate loads.
And the good part about that is because it's pluggable for any data store, you can have your own data model and it works. You just have to define that schema and you can just generate load. You specify the payload and it works beautifully. Instagram folks have been using it. Any other questions? Cool. Thank you very much for coming. I think that concludes our meetup today.